All right, well, let's keep going on then. So we were talking about position last time. We got into, you know, we started particle kinematics. Along a line. And I started by talking about position. And to come up with a numeric position, you need to choose two things, a zero position and a positive direction. And once you have the position defined, you can define displacement. It's related to position. If you choose two instants, T1 and T2, then the displacement between those two instants and I'll call it lowercase d, is the position at the later time minus the position at the earlier time. A couple of things to notice about the displacement. Displacement has two pieces of information in it. The first one is the absolute value of the displacement, the magnitude of it. Is the distance between the two locations. And the sign is the net direction the object is moved over that time interval. Okay, so again, this sign you can think of as you can always think of the sign, which is, the sign is a mathematical thing. As equivalent to an arrow in the space where the motion occurs. So the sign is, like in math world, the space where the motion occurs is in, the real world. Okay, so let's say that you have an object moving around on the floor. And let's say we're calling this the positive direction. Okay. And let's say that the motion of this object, and we would have also had to choose a 0 position somewhere. Let's say that we'll call this the 0 position. And the position of the object over time is given by the function p of t is equal to 2t cubed minus 20. Let's say this is in meters. Okay, so first, what's the displacement from time equals 0 to time equals 20? Oh no, that would be big. Time equals 1 second. What's the distance between the locations at these two instants? And third, what direction is the arrow in the direction of the object's net motion? Okay, so to figure out the displacement, we have to figure out the position at these two instants. So the position at time equals 0 is 0 cubed times 2 minus 20, so negative 20. The position at time 1 second is 2 times 1 cubed minus 20, so negative 18. And since this is all given in meters, the units are meters for each of these. And so the displacement is just the position at the later time minus the position at the earlier time. That's negative 18 minus negative 20. So that's positive 2 meters. Okay, so what's the distance between those two locations? The distance is the absolute value so again, that's 2 meters. And the net direction, well, it's a positive sign, so it's moving in the positive direction. So now back in the real world, the world where this object lives, the positive direction is to the right, so the arrow is to the right. In fact, one way you could think about this, and this is what vectors are when we get to vectors, is you could think of this arrow having a length that represents the magnitude. You know, if it's 2 meters, it's this long. If you did this for 2 different times and it was 15, then it would be, that much longer. So the arrow would represent the magnitude, the length of the arrow, and the direction it's pointing tells you the direction. Okay. So we're in one dimension now with motion along a line, but we're going to have to use that vector idea when we get out of motion along a line. Okay, so displacement as units of length, just like position does, because you're just subtracting. Any questions about that? So next, we're going to define instantaneous velocity. And if the position over time is given by the function p of t, then instantaneous velocity as a function of time is the time derivative of the position. And by the way, in mechanics, time derivatives are common enough that people give this a shorthand. So if you ever see something with a dot over it like this, that means take a time derivative of it. That dot always means time. When you show a prime on something, that means the derivative with respect to whatever the independent variable is. A dot is always time. The units of velocity are length over time. And so that means that in SI units, it's meters per second. Okay, like miles per hour is what we're most used to thinking of, but in SI units, meters per second. And here's some things to recognize, to notice about the instantaneous velocity. First, the absolute value, or the magnitude, of the instantaneous velocity is the instantaneous speed. So if the velocity is negative 48 meters per second, it means it's moving at a speed of 48 meters per second. And just like with all the directional quantities that we deal with, the sign tells you the direction. In this case, the sign tells you the direction that the thing is moving at that instant. And again, just like displacement, that sign is equivalent to an arrow in the object's world. Okay, so if we choose this to be the positive direction, okay, and then at an instant, an object has a velocity of negative 30 meters per second. That means at that instant, it's moving with a speed of 30 meters per second. That's what its speedometer would say. And since it's negative, I said it's negative, right? Since it's negative, it's moving opposite what we chose as the positive direction, so it's going this way. Okay. And the last thing is, since we talked about position versus time graphs before, on a position versus time graph, V is the slope of the tangent at that chosen instant. So let's think of an example. So if an object moves according to a position function of, let's say this is like 2 times t minus 3 squared. Okay. And let's say this is given in meters. Let's first sketch the position versus time graph. Based on that sketch, let's figure out when the object is moving in the negative direction, the positive direction, and when it's stopped. So when's it moving in the negative direction, the positive direction, and when is it at rest? Okay, and then we'll figure out what direction is the object moving at the instant t equals 2 seconds. And actually, yeah, might as well just calculate the velocity at that instant. Okay, so to sketch this graph, the position is going to be 0 when time is equal to 3. So 1, 2, 3, 4, 5, 6. Okay, so that's the position there. At time equals 0, what's the position going to be? 18. So let's say this is 10, this is 20. So it's going to be, somewhere here. At time equals 6, what's the position going to be? Also 18. And it's a parabola, so it's going to look something like this. Okay, so these times they're 0 time, 1 second, 2, 3, 4, 5, 6. And by the way, there's no mathematical reason, obviously, like you've always dealt with functions that have negative values. There's no problem with a function having negative independent variable values. In physics, we just don't use negative times. There's no reason that's true, but nobody does, so we're not going to do it either. Okay, so we're going to imagine that time equals 0 is when this motion starts, or when our interest in this motion starts. So what's the time interval where this object is moving in the negative direction? Yeah, 0 to 3, because if you think of the slopes of the tangent lines of all these points, those slopes are all negative. Okay. They're getting closer to 0 as you go. So this object is moving in the negative direction on the interval from 0 to 3. Is there any place where this object has 0 velocity? Yep, at t equals 3. So that's where it's at rest instantaneously. It has 0 velocity. And then when is it moving in the positive direction? Yeah, as far as we go. Yep, exactly. So 3 to infinity, or 3 to 6, the way I drew it. Based on this graph, where are the places where the speed is the greatest?
At the start, or it gets infinitely faster.
So this is 0 slope. The absolute value of the slope is speed. And so the biggest absolute value of the slope is as you get closer to 0 and as you get closer to 6, right? And it slows down as you get closer to being at rest, and then it speeds up again as you go away. And then, so let's calculate for part C, the velocity at time equals 2 seconds. So to do that, we're going to go back to the function. Where's this? Okay, so our position function is 2 times the quantity t minus 3 squared. To calculate the velocity as a function of time, that's the time derivative of the position as a function of time. And so that's equal to 4 times the quantity t minus 3. And then the chain rule says you have to take the time derivative of the stuff inside the parentheses, which is just 1 in this case. So we get 4 times the quantity t minus 3. So now the velocity then, if you want to find it at a specific instant, now that we have the function, you can just plug it in. So the velocity at 2 seconds is 4 times the quantity 2 minus 3. So, yep, negative 4 meters per second. And the negative means it's moving in the negative direction at that instant. Yep.
Are we going to be required to show our units as we do our work, or
No.
just for the final answer?
Yeah, just for the final answer is fine. Any questions about any part of that? All right, well, that's instantaneous velocity. And now we have to define acceleration. And just like velocity is a measurement of how quickly the position is changing, the acceleration is a measure of how quickly the velocity is changing. So it measures how quickly the velocity is changing. And the definition of the acceleration as a function of time is the time derivative of the velocity function which you can also think of as d dt of the velocity function. And that means that it's the second time derivative of the position function. Or you can write it this way. The units for acceleration are length over time squared. And that means that the SI units are meters per second squared. And let me go back here for a sec. Okay, so there's a few things to keep in mind about acceleration. So notice so the first one is on the position versus time graph, The acceleration is the concavity of the graph. So if the P versus T graph is linear at a chosen instant, then the acceleration is equal to 0 there. That's an inflection point if you have a graph that's curving. If the P versus T graph is concave up, at the chosen instant, then A is positive. So that's if you're talking about something like that. It looks like the mouth of a person with a positive mental outlook. And if the P versus T graph is concave down, at the chosen instant, then the acceleration is negative at that instant. Okay, so now what does acceleration tell you physically? When we talked about velocity, we talked about if the velocity is positive, it means the object at that instant is moving in the positive direction. If it's negative, the object's moving in the negative direction. What does it tell you if you have positive or negative acceleration? Well, in motion along a line, for motion along a line, changing the velocity, all it can do is change the speed of the object. The object can't move off the line, so it's not like it can turn right or something, you know what I mean? So non-zero acceleration always means the speed is changing. We'll see when we get to two-dimensional and three-dimensional motion that that's not true necessarily, because since objects can change their direction, the velocity can change even if the speed is staying the same. But for now, a non-zero acceleration means the speed's changing. So what do you think it would take for the acceleration to tell you that the object's speeding up? Maybe the first thing that would pop into your head is like positive acceleration. Yep.
The acceleration and the velocity have to be of the same sign.
Yep, that's exactly right. So if the velocity and acceleration have the same sign, the object is speeding up. Which direction is it speeding up? Well, you can get that from the sign of the velocity. So if they're both negative, since the velocity is negative, it means the object's moving in the negative direction and speeding up, okay? If they're both positive, it means it's moving in the positive direction and speeding up. If the velocity and acceleration have opposite signs, it means the object is slowing down. And again, you can tell what direction it's going from the velocity. What's it doing if the velocity is 0 and the acceleration is, say, negative? Yeah, once you're at 0 velocity, you can't go any slower. So it's definitely speeding up, and it's starting to move in whatever direction the sign of the acceleration is. So that means that it would be starting to move in the negative direction, but it hasn't built up any velocity yet. These derivative relationships for velocity and acceleration, where is that? So that also tells you there's an integral relationship. If you know the acceleration, you can integrate with respect to time to get the velocity. You have to, in that case, deal with constants of integration, and I'll talk about how to do that. Yep. With respect to time. Yep. So in any context, if you see the dot over the top, it means it's a time derivative. Whereas a prime is not specific. It just means it's a derivative with whatever the independent variable is. Okay. So let's say that we have a position versus time graph. So let's say that the position versus time graph is this. Let's say it starts here, does that. Okay. And let's say that that represents a motion let's say of an object moving along like a ramp. And let's say the 0 position is here and the positive direction is this way. Okay, so first, over what intervals is the object moving in the positive direction? Sorry, I'm going to draw this a little more. So I'm just going to break this up into, I'll make an inflection point there and here, and let's call these points, so that's 0. Let's call this A, B, C, and D. So over what intervals is it moving in the positive direction? Well, yeah, actually, I mean, it's sort of, it's not perfect, but yeah, I'm sort of thinking of this as the only place that it's horizontal is at time equals 0 on this side. So the slope is positive all the way from 0 to B. Okay. So So it's moving in the positive direction from 0 to B. So now let's draw an arrow in the direction of the motion at interval from 0 to B. So now we're switching from this totally mathematical thing to putting an arrow in the real world that represents this motion. Which way is it going? It's going in the direction that we chose to be positive, which is left and up. Yep. Question? Okay. Any questions about that? The connection between the sign in math world and the direction the thing's moving. So and now over what intervals? So I'm going to not write down the questions about when's it moving in the negative direction, but that's just going to be the, from B to D and on. So when it's during that interval from B to D, it's moving in the negative direction. What's an arrow in the direction of that motion? Yeah, it's going to be just opposite the positive direction. Okay, so now over what intervals is the acceleration? Let's do negative on this one. Yeah, so we're looking for places where it's concave down. And so it's going to be from the inflection point at A to the inflection point at C. Okay, everywhere else it's concave up. And now one more question. When is the object speeding up? Well, there's kind of two intuitive ways to think about this. One is to think about, is it going from closer to zero slope to farther from zero slope? Because that would be speeding up. Or is it getting closer to zero slope? That would be slowing down. Or you can just, over all these different intervals, think about the sign of the velocity and the acceleration. And when they're the same, it's speeding up. When they're opposite, it's slowing down. So from 0 to A, the slope is positive, right? Velocity is positive, concave up. They're both positive, so it's speeding up from 0 to A. Okay. And B to C, that's right. Those are the two places where it's speeding up. From A to B, it's slowing down because the slope is positive, but it's concave down. So you have a positive and a negative. Then it's speeding up here because it's a negative slope and a negative and concave down. Okay. And then slowing down again and getting back to zero velocity, slowing down, starting with a high speed and getting to zero speed. So the two intervals are 0 to A and B to C. Any questions about that? Well, let's stop there. I'll put some new problems up tonight. If you haven't gotten to the ones I assigned yesterday, just if you can stay one class within one day of when I assign the stuff, that would be fine. I usually post the stuff the night, so you don't have a ton of time to get it done, before the next class. But lagging behind one day is no problem. But just do this stuff, put it in your binders, and bring questions if you have any trouble with any of the problems I assign. Okay.
The first binder check, is that like late February?
I think it is. It's in the syllabus. Yeah. Okay.